We'll start in about a minute. In a few minutes, we'll start section 11.6. This has three tests. One is the absolute convergence test. Another one is the ratio test. And then the third one is the root test. But first, we'll look at the last three series that we were looking at last time, involving alternating series. We started this one. So this series can be rewritten by simplifying 2 to the 2n minus 1 in the numerator, which is 4 to the n minus 1. And then apply the alternating series. Before doing that, I'll just remind you of the alternating series test. If you have an alternating series, and if it satisfies these two conditions, so if b sub n plus 1 is less than or equal to b sub n for all n, that means the b sub n sequence is decreasing. And if the limit of b sub n as n approaches infinity is 0, then the alternating series converges. Okay, so on this one, the second condition is not satisfied. So we note that the limit as n approaches infinity of 4 to the n minus 1 divided by 4 to the n equals 1. And since that's not equal to 0, we cannot conclude anything about this series by using the alternating series test. Okay, but if we apply the test for divergence, we can try that to see if that works. Okay, but for the test for divergence, we have to take into account the negative 1 to the n plus 1. In other words, we have to compute the limit of the terms from that series. Well, even with the negative 1 to the n plus 1, as n approaches infinity, the even terms approach, when n is even, those terms approach negative 1, and when n is odd, those terms approach positive 1. So this limit doesn't exist. Up here we saw that without the negative 1 to the n plus 1, this term approaches 1. So this limit doesn't exist because half of the terms are approaching positive 1, the other half are approaching negative 1. So this limit does not exist. And so for the test for divergence, we conclude that this series does not converge, that it diverges. So this series diverges by the test for divergence, not the alternating series test. Okay, the next example, the infinite series, the terms are -1 to the n times 1 divided by the cubed root of n squared plus 1. So the terms b sub n without the -1 to the n are just 1 over the cubed root of n squared plus 1. So does this sequence decrease as n increases? So the next term after that is 1 over the cubed root of n plus 1 squared plus 1. So it's pretty clear that this denominator, the cubed root of n plus 1 squared plus 1, this denominator is bigger than this one. So that must mean that this term is smaller than that one. So it satisfies the first condition of the alternating series test. And then we want to know if the limit of b sub n is equal to 0. So just to be clear, condition 1 of the alternating series test is satisfied. And then the second condition, if we take the limit as n approaches infinity of the b sub n terms, well, it's pretty evident that the denominator approaches infinity. So 1 over a number that's approaching infinity approaches 0. So that means condition 2 of the alternating series test is satisfied. And so the series converges by the alternating series test. Okay, the third example, the infinite series of cosine of n times pi divided by 1 plus 1 over n. So this is listed as an alternating series, and you can see what cosine of n times pi does as n, when n is an integer. When n is 1, cosine of pi is -1. When n is 2, cosine of 2 pi is +1, and so on. It just alternates back and forth. So this is sort of an obnoxious way to write something equivalent, which is, I'll just do that. Replace cosine of n pi with -1 to the power n over 1 plus 1 over n. Okay, so it's an alternating series. or the b sub n terms getting smaller. So we take out the negative 1 to the n, write 1 over 1 plus 1 over n. So is this sequence decreasing? Well, if we do a little algebraic maneuver here, notice in the denominator, 1 plus 1 over n, if I find a common denominator n, I can replace 1 plus 1 over n with n plus 1 over n, n plus 1 all over n. And 1 divided by n plus 1 over n is n over n plus 1. So as n increases, do these numbers n over n plus 1 decrease? They don't. No, they don't. So n over n plus 1 approaches 1, but it's increasing to 1. Yeah. Yeah, if you just look at the first two terms, when n is 1, you have 1/2. Then when n is 2, you have 2/3. It's increasing. So b sub n does not approach 0. So the alternating series test doesn't tell us anything. So I'll just make a note, since the limit of b sub n, of the b sub n terms does not equal 0, we abandon the alternating series test. Remember, the alternating series test only tells us when an alternating series converges. It doesn't tell us anything about divergence. So we have to use a different method. Okay, so once again, the test for divergence will tell us that this series diverges. So when we apply the test for divergence, we have to take the limit of the terms from the series, not just the positive ones like we do in the alternating series test. But we can rearrange it. We simplified the 1 over 1 plus 1 over n to n over n plus 1. So we can write this as negative 1 to the n times n over n plus 1. So the terms alternate between positive and negative, or vice versa. So what do you suppose is true about this limit?
Does it also not exist?
What's that?
Does it also not exist?
Yeah, it does not exist. Without the negative 1 to the n, we all agreed that n over n plus 1 approaches 1, positive 1. But since the terms alternate between positive and negative, half of the terms approach positive 1, the other half of the terms approach negative 1, so the limit does not exist.
Question, Professor, just out of curiosity, if in instances where the alternating series test doesn't tell us if it's convergent.
Can you speak up a little?
Sorry. In instances where the alternating series test doesn't work and we have to go to the test for divergence, will it always show that it's divergent because of the alternating pattern like that?
Oh, okay, so the question is, if the alternating series doesn't work, alternating series test doesn't work, will it always be the case that the test for divergence works? Is that what you're asking?
Yes.
Well, I've suspected that, but I haven't seen every possible alternating series.
That's fair, yeah.
So I suspect that, but I'm not going to make a claim that it always does, because I haven't seen everything
Yeah.
that could possibly be done.
Just notice the pattern, that if the alternating pattern like that
Yeah.
caused the limit to always diverge like that, I was just wondering if that would pretty much always be the case, but I was just curious.
Yeah, like I say, I suspect that it always is, but I'm not going to say that it always is. As soon as I do, someone will show me a counterexample. So we'll just take it case by case.
Well, thank you.
Good. Yeah, so this limit does not exist. And so we conclude that the alternating series diverges because of the test for divergence. Okay, now we can start section 6. So we have 3 tests, 3 convergence tests in the section 6. One is the absolute convergence test, the other one is the ratio test, and the third one is the root test. So we start with a definition. An infinite series is called absolutely convergent if the series of the absolute values is convergent. So if a series has all positive terms, that's what I'm saying here. In the case that a sub n is greater than or equal to 0 for all n, then the absolute value of a sub n is equal to a sub n for all n. And so absolute convergence is the same as convergence in those cases. Okay, so if it turns out that some of the terms are from an infinite series are positive and other terms are negative, then this question about absolute convergence is going to be useful. So let's note this one, the alternating series. We have the terms are -1 to the n plus 1 divided by the cubed root of n to the 4th. This one is absolutely convergent because if we take the absolute value of the terms, we can ignore the -1 to the n plus 1 and just look at the series of 1 divided by the cubed root of n to the 4th. We know that this series is convergent because it's a p series with the value of p equal to 4/3, and 4/3 is greater than 1. So that means that this original series is absolutely convergent. And here's an example of an alternating series that is divergent. I should say it's not absolutely convergent. Well, let's just read it. Okay, this series where the terms are -1 to the n over 2n minus 1 is not absolutely convergent because when you take the absolute value of the individual terms, you get the series where the terms are 1 over 2n minus 1. And this infinite series is divergent. We can compare it with this divergent infinite series where the terms are 1 over 2n. So I'll just make a note of this one. This is equivalent to thinking of multiplying 1/2 times the harmonic series. And the harmonic series diverges. Okay, another note. Does this alternating series converge even though it's not absolutely convergent? Yeah, so the positive terms are 1 over 2n minus 1, and that sequence decreases. And b sub n also goes to 0. So the alternating series does converge, but it does not converge absolutely. So it converges by the alternating series test, but it's not absolutely convergent. Okay, here's another definition. A series is called conditionally convergent if it is convergent, but not absolutely convergent. Okay, so this series is convergent, but not absolutely convergent, so it's conditionally convergent. Okay, I don't plan on giving you a vocabulary test, but be familiar with the terms enough that you'll know what it's saying when you're reading about them in the textbook. Okay, so here's another example. The alternating harmonic series is conditionally convergent. That is the infinite series where the terms are -1 to the n plus 1 times 1 over n. We showed or observed that this is convergent using the absolute, or I should say the alternating series test. But in absolute value, we're looking at the harmonic series, which we know diverges. Hey, here's a theorem that's going to be of great use. If a series is absolutely convergent, then it is convergent. So here's a sort of just a short sketch of a proof. For any infinite series that have terms a sub n, this inequality will be true for all n. 0 is less than or equal to a sub n plus the absolute value of a sub n. And this will be less than or equal to 2 times the absolute value of a sub n. So this compound inequality will hold for any series. Okay, if a series is absolutely convergent, so that's what we're given, that's the hypothesis. So we're given that the series is absolutely convergent. So this converges. So the series of 2 times the absolute value of a sub n also converges. By the comparison test, this series, a sub n plus the absolute value of a sub n, this converges by the comparison test because the terms are less than or equal to 2 times the absolute value of a sub n. And so the series of the a sub n terms is equal to the difference of 2 convergent series. Okay, for all n, we note that a sub n is equal to a sub n plus the absolute value of a sub n minus the absolute value of a sub n. So we're no doubt all in agreement about that. But since these 2 series are known to be convergent, this one converges and this one converges. And a few days ago, we saw one of the properties of infinite series. If 2 series both converge, then their difference also converges. But the difference is this series of a sub n terms. So if you can remember that if a series is absolutely convergent, then it is convergent, that's what you'll want to remember. All right, let's look at the next page. Test this series for absolute convergence. So this series, the terms are sine of 2n minus 1 times pi over 2, all divided by n to the third. So when you start investigating the sign of those terms, when n is 1, we have 2 times 1 minus 1 is 1 times pi divided by 2. Sine of pi over 2 is 1. When n is 2, 2 times 2 is 4, 4 minus 1 is 3, 3 pi over 2 is negative 1. So this is another one of those alternating series that can be written in a simpler form. So why don't we do that? The terms are alternating between positive and negative. So from n equals 1 to infinity, in the numerator, we can write negative 1 to the n minus 1 over n to the third. Okay, the question is, does this infinite series converge absolutely? Okay, so in absolute value, the term becomes this infinite series where the terms are 1 over n to the third. So what do we know about this infinite series where the terms are 1 over n to the third as n ranges from 1 to infinity? It's a p-series. The value of p is 3, and 3 is greater than 1, so it's convergent. Yeah, so this is a convergent p-series where p is equal to 3, which is greater than 1. So the original series converges absolutely, therefore it converges. So make a note of that. Since the original series converges absolutely, it converges, or it also converges, whatever. Okay, the next test is the ratio test. So this one says if the limit as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n, if that limit exists and is less than 1, then the series of the a sub n terms is absolutely convergent. And if the series is absolutely convergent, then it's convergent. So maybe I should have written that in there. It is spelled out in the textbook. If this series is absolutely convergent, and is itself convergent by the theorem. Okay, on the other hand, if the limit of the ratio of the absolute value of the ratio a sub n plus 1 over a sub n exists as a finite number greater than 1, or if the limit of the ratio of the absolute value of the ratio is positive infinity, then the series is divergent. Okay, but if the limit of the absolute value of the ratio a sub n plus 1 over a sub n is exactly equal to 1, then the ratio test is inconclusive. So we have to use a different method if we get that result from the ratio test. Okay, in this example, let's use the ratio test to test the series. So just as a reminder, in the numerator, we have the n plus first term from the sequence, and in the denominator, the nth term from the sequence, and then we take the absolute value. All of these numbers are positive, so we don't really need the absolute value symbols. So a sub n plus 1 is going to be n plus 1 to the 10th divided by 10 to the n plus 1. This is the a sub n plus first term. And we divide it by the nth term, which is n to the 10th over 10 to the nth. So let's simplify this a little bit. n plus 1 to the 10th over 10 to the n plus first times 10 to the nth over n to the 10th. After we simplify this a little bit, we'll take the limit to see what we get. Okay, some pretty nice cancellations are going to take place. Notice in the numerator we have a factor of 10 to the nth, and in the denominator 10 to the n plus first. So 10 to the nth divided by 10 to the n plus 1 is 1 over 10, right? So I'll put 1 over 10 for this part. And then in the numerator, we have n plus 1 to the 10th. In the denominator, n to the 10th. So I'll just, for now, for this step, I'll just write n plus 1 to the 10th over n to the 10th. And then write the next step as 1/10 of the quantity n plus 1 over n to the 10th. Okay, so now we take the limit of that as n approaches infinity. And what do we get? Well, the limit of n plus 1 over n as n approaches infinity is 1. So 1 to the 10th is 1, and so 1/10 times 1 is 1/10. So this limit is less than 1, and so the ratio test tells us that this series is absolutely convergent. Well, it's convergent. So in this one, absolute convergence is the same as convergent. So by the ratio test, this series converges. Pretty neat, huh? Okay, the next page we'll look at the root test. The root test. If the limit of the nth root of the absolute value of a sub n as n approaches infinity is equal to a finite number less than 1, then the series of the a sub n terms is absolutely convergent. On the other hand, if this limit of the nth root of the absolute value of a sub n is equal to a finite number greater than 1, or if that limit is equal to infinity, then the series is divergent. And then part 3, if the limit of the nth root of the absolute value of a sub n is equal to 1, then the root test is inconclusive, so we would have to find a different method to test the series. So the root test usually works pretty nicely in the examples you'll see. So use the root test to evaluate this series. So the limit as n approaches infinity of the nth root. Well, all of the terms are positive. We don't need to put absolute value symbols around them. So the nth root of 2 to the n over the quantity n plus 2 to the n. Okay, when we take the nth root of 2 to the n over n plus 2 to the n, we're just going to get 2 over n plus 2. And what does that limit equal? 0. Yeah, the numerator gets, or the denominator gets big. The numerator is a constant, so the limit is 0. So we conclude that this series converges, or it's absolutely convergent, but same as convergence in this case. So the series converges by the root test. Okay, the next one, I'll give you a few seconds to work on this one. Just apply the root test and see what you come up with. So you can type in an answer online if you're watching. All done? What'd you get?
I got divergent.
You got
Divergent.
divergent
I got divergent
by using the ratio test?
by using the root test.
Sorry, yeah. Yeah, by using the root test. And you got
I got 1, so it would have been
you got the limit equals 1, so that means inconclusive if the limit is 1.
I think I might have made an error.
Is that what you got?
I think I may have made an error actually, so disregard. what
Okay.
I did. I think I just realized.
Okay, well, let's see what happens. One of you is correct. Okay, so the root test, the limit as n approaches infinity of the nth root of the absolute value, these are all positive, so we don't need the absolute value. 1 plus 1 over n to the n. And the nth root of something to the nth power is just that something. So 1 plus 1 over n. Yeah, we can evaluate this limit. 1 over n goes to 0, so 1 plus 0 is 1. So the root test is inconclusive.
Embarrassingly, I realized when I was doing it mentally, I forgot to take the limit and I went to a completely wrong answer. So that's where I made an error. You were right.
Okay, root test doesn't work. So, any other ideas? How about the test for divergence? Well, let's see what happens. Test for divergence. So if we compute the limit of the terms, so 1 plus 1 over n to the n, So you might have seen this before, possibly. So this limit is the number e. If you took college algebra here, you might have seen that expression when you were deriving the continuous compound interest formula. This expression pops up in the derivation of that formula. But this limit is equal to e, and since e does not equal 0, we conclude that this infinite series diverges by the test for divergence. So the series diverges. Okay, let's look at the next infinite series. So we have this infinite series. The terms are n over the natural log of n to the n, starting at n equals 2. So we're getting a number of different tests to apply. Which one do you think might work in this one?
The root test?
Yeah, let's try the root test, because in the denominator we have the quantity, the natural log of n to the nth. So let's try the root test. Try the root test. If that doesn't work, we can try something else. So the limit as n approaches infinity of the nth root of the absolute value of n over the natural log of n to the n. So the limit as n approaches infinity. In the numerator, the nth root of n is n to the 1 over n, and n to the 1 nth. And then the nth root of the natural log of n to the n is the natural log of n. Okay, so we've seen enough this semester to know what the numerator approaches. As n approaches infinity, n to the 1 over n approaches 1. And the denominator approaches infinity. And so 1 over infinity is really a very informal thing to write, but we say that the limit is 0. So the limit is 0. Well, 0 is less than 1. So by the root test, the series converges. Okay. Let's try the next one. The infinite series of 2n factorial divided by n factorial squared. So what test should we use this time, you think?
A comparison test?
The what one?
A comparison test?
Well, I was thinking maybe the ratio test.
That was my second choice.
Let's try the ratio test. So that's the n plus first, whoops, a sub n plus 1 divided by a sub n. So I'm going to omit the limit notation momentarily. So on this one, you have to be a little careful. if I replace n with n plus 1, I get 2n plus 2, because 2 times the quantity n plus 1 is 2 plus 2, 2n plus 2. So 2n plus 2 factorial over n plus 1 factorial and then squared, and then divided by 2n factorial over n factorial squared. So 2n factorial over n plus 1 factorial squared times n factorial squared over 2n factorial. So we're out of time. So work on that. Maybe on Monday we'll finish this one and the next one. But that's all for today.